Hello and welcome friends. In this particular module, we wish to discuss some of the things related with the permanent adjustments of theodolite. So, we will get introduced with the fundamental axes of the theodolite and their relationship. We will also discuss about the conditions to satisfy as well as tests to perform for the various adjustments. We will also discuss about the procedure to follow in order to bring that particular fundamental relationship into existence. So as you learn the content, you will be able to demonstrate the fundamental relationship among the axes of theodolite. Also, check the fundamental relationship among the axes of theodolite and state the procedure to establish that fundamental relationship among the axes of the theodolite. In the module construction and basic definitions, we have already discussed about these particular constructional aspects of theodolite. As you know, there is a vertical axis of the equipment about which the equipment rotates. There is horizontal axis of the equipment about which telescope rotates in the vertical plane. For the plate levels, when brought at its center of the run, its crown point defines the plate level axis. For the telescope, the horizontal axis can be defined as line of collimation, line of sight, or also axis of telescope. As we consider this particular altitude level tube, its position and when bubble center gives this particular axis of altitude level tube. As you know, in a perfectly conditioned equipment, there must be a definite relationship among the axes that we discussed. So, here this particular vertical crosshair should lie in a plane perpendicular to the horizontal axis. The axis of each plate level should lie in a plane perpendicular to this vertical axis. The horizontal axis should be perpendicular to this vertical axis. The axis of telescope should be parallel to the line of sight, or when axis of altitude level tube is horizontal, vertical circle should read 0 and the line of sight should be horizontal. The line of sight should be perpendicular to the vertical axis. Also, the axis of telescope as well as line of sight should be overlapping each other. Every theodolite is said to be in permanent adjustment if it satisfies all the relationship that we discussed. However, because of mishandling of the equipment or otherwise its wear and tear, the state of relationship may get disturbed. Hence, one should check this particular relationship periodically as well, establish that particular fundamental relationship among the axes as and when required. These permanent adjustments are based on the geometry of this particular fundamental axis. Hence, as one adjustment is done, it may disturb the other adjustment. Hence, it is expected to have this particular relationship re-established in definite order. So that order is, first we have to adjust this particular vertical crosshair, then go for the adjustment of this particular plate level axis. Thirdly, we'll be going for adjustment of line of sight. Then we'll be going for adjustment of this particular horizontal axis and the adjustment of axis of telescope and adjustment of vertical circle index follows this fourth adjustment. So the first adjustment, here the vertical crosshair should lie in a plane perpendicular to the horizontal axis. So the way you see here, this is nothing but the vertical crosshair, whereas this is nothing but the horizontal axis. So this particular vertical crosshair should be perpendicular to this particular horizontal axis. It can be assessed very easily in field. So we can keep this particular equipment, say at a distance of about 40 to 50 meters away from vertical surface. We can define a well-defined point on that particular, say, vertical surface, and we bisect that particular point with the reference of this particular vertical crosshair. Now, we can clamp the motion by clamping the upper as well as lower clamp, and as we rotate the telescope vertically in slow manner, we expect that point to travel exactly along that particular vertical hair. So here, if this particular movement of that particular point appears along this particular vertical crosshair all the way, the vertical crosshair is perpendicular to this particular horizontal axis. If not so, this vertical crosshair should have been tilted and hence it needs to be adjusted. So as discussed in the constructional aspects, this diaphragm is fitted by making use of 4 such capstan headed screws. So here we can loosen this particular adjacent capstan headed screws and we can rotate that particular eyepiece in the requisite manner such that the point will be exactly lying on that particular vertical crosshair all the way. So we can repeat this particular test again, and if required, maybe adjustment redone. Second adjustment is related with the axis of plate level. Ideally, the axis of each plate level should lie in a plane perpendicular to the vertical axis. This adjustment test is very similar to the adjustment that we discussed for dumpy level in the leveling chapter. So here we can carry out the leveling operation the way the way we carry out our temporary adjustment by keeping the telescope parallel to any 2 hood screws and having the second position as perpendicular to the earlier position and by making the bubble traversing. So in this case, if the bubble is not remaining at the center, then the equipment is not in adjustment. So here we bring that particular position of the bubble at the center of its run by making use of two foot screws, whereas the remaining half needs to be adjusted by making use of these particular capstan headed screws. So as we reassess, as we re-perform this particular test, for initial position and second position, the bubble should remain at the center of the run only. As we turn the telescope about the vertical axis, so as it attains various positions in the horizontal plane, all the way bubble should be remaining at the center of its run. If so, the adjustment is in order. If not, we need to readjust the equipment. Third adjustment is of line of sight. So, for a properly adjusted instrument, the line of sight should be perpendicular to the horizontal axis. So, in order to check whether this particular adjustment is in order, say the equipment is kept at station O and it is exactly centered over the station O, temporary adjustments are done. Now, by clamping upper as well as lower plate, let's have sight at some station X, we say some 100 meters away from the instrument position. So as we sight this particular position of X with face left condition, now place the telescope and mark a point on, say, vertical surface which is situated at 100 meters, and this marking would be approximately same level as that of station X. Now, by loosening the lower plate, let's have the equipment rotated so that this X station will be rebisected with now face right condition. So clamp the equipment, again place the telescope and mark the point. So after plunging and marking these particular position on vertical surface with face left and face right condition, we should get one and same position as seen as Q here. If this happens, the line of sight is perpendicular to the horizontal axis. If not so, we have to perform the adjustment. So say with face left condition we are getting this particular location Y, and say with face right condition we are getting this location Z. So when the condition V is with, say, face left, this particular line of sight is making some inclination of E with the horizontal axis. As such, it is not exactly perpendicular. Hence, on the opposite side, there has to be 90 minus E angle. As we alter the position of this particular face, the angle, say here, this particular ZOB will also be 90 minus E. As we try to work out here the angle QOZ in order to have that particular line of sight perpendicular to the horizontal axis, this 180 minus 90 minus E minus 90 minus E is computed as 2E. As such, Here, with the face left condition and with the face right condition, as the markings y and z are done, the total distance in between the station y and z as marked would be 4e. As such, we have to locate say point P at distance 1/4 of this particular say total distance of 4e, which is nothing but e. Now in order to have this, we have to move the crosshair ring by making use of two opposite horizontal screws, so that the line of sight will be passing through this particular station P. Then these particular screws will be tightened and we will repeat this particular test and also adjustment till the line of sight is observed to be perpendicular to this horizontal axis. That is, whenever we place the telescope on opposite side, we should get the same location of this particular station Q. This is fourth adjustment. According to this, the horizontal axis is required to be perpendicular to the vertical axis of the equipment. Let's assume that equipment is set at some station situated at about say 50 to 60 meter from a vertical wall. Let's bisect well elevated position say 40 to 45 degrees above the horizontal plane as x, with both the motions clamped in the horizontal plane. Let's have the telescope moved in the vertical plane. So here, say with the face left condition, station X is bisected, telescope is rotated in the downward manner, and some marking is done on that particular vertical surface at ground level. Now change the face of the equipment and re-perform these. That is, with the face right condition, bisect station X, clamp the horizontal motions, rotate the telescope in the vertical plane. As the line of sight comes to the ground level, mark the point. Here, with both the faces, this X as projected at the ground level should be giving the marking as say Q. If we are not getting the same location marked as Q, that means say with the face left condition we have got that particular location as Y, and with the face right condition we have got that particular location as Z. So work out the midpoint of that particular YZ as Q now. Bisect that particular station Q and elevate the telescope vertically so that the line of sight will be just adjacent to that station X. So here this particular difference is to be nullified. In order to do so, here we'll be making use of this particular capstan headed screw provided at the adjustable end of the horizontal axis. So, as we loosen that, we can lift or adjust that particular bearing cap such that this particular vertical crosshair will be exactly passing through this particular station X. So, according to the requirement, as we raise or lower that particular Saturnian axis, it is quite probable that the vertical crosshair may get disturbed. So, after each movement of this particular adjusting screw, the location of Q on that particular lower ground level should be checked and needs to be adjusted by making use of horizontal tangent screw. This particular adjustment is also called as spire test. The fifth adjustment is for axis of telescope. This is again very similar to the adjustment that we discussed for W level. Here, the condition is the line of sight should be parallel to the axis of bubble tube. So, in order to check that, we have two stations A and B set at say 60 to 90 meter away. We keep the equipment exactly midway between. With the equipment level, we take the reading as A and B on station A and B respectively. As such, we determine the true difference in elevation h because here the line of sights are balanced. Now, in the same line AB, as we keep the equipment at station Y, say at 10 to 15 meter away, and as we take the readings C and D after carrying out the temperature adjustment at Y, we'll be getting apparent difference H dash. The true difference that is worked out as H and the apparent difference that is worked out as H dash should be one and same in order to say the line of sight is parallel to axis of bubble tube. So if this particular H is not equal to H dash, that means we have to perform the adjustment. This particular adjustment can be done with two approaches. Say here, this is the first case in which the equipment is kept at station D1 with respect to A in line of AB. So here, as we consider the set of lines, as we consider this particular set of lines, here error at station A by D1 should be equal to this EB by D plus D1 should be equal to EB minus EA over this particular distance D, which is nothing but error E. So as we follow this particular equation, we will be able to work out the correct stop reading required, say at station B, when the equipment is situated at distance D1 with respect to this A. Here, this error is H minus H dash. In turn, it is nothing but the difference in the true difference in the stop readings and the apparent difference in stop readings as that are obtained as shown here in this particular figure. So this error E occurs in a distance of D. So let's assume that this particular error is positive and the line of sight is inclined upward. The error in distance d plus d1 is EB, which as discussed here should be equal to E into d plus d1 by d. Hence, as we work out this particular error at B from observed staff reading B1, it can be deducted in order to get the correct staff reading which could have existed when the line of sight is horizontal. After calculating this correct staff reading, now the capstan screws at the top and bottom of the diaphragm ring are loosened and the ring is rotated vertically downward so that the line of sight will be passing through that computed reading. So, as this particular adjustment is done, further we can check the adjustment. We can take the reading on, say, staff A. It should be A1 minus EA, the way it is computed by making use of this particular expression. So, this A1 minus EA requirement, if not satisfied, then this particular adjustment is repeated such that we'll be getting H is equal to H dash. So this method, as discussed previously, is nothing but a two-peg test. One must take into account the sign throughout all the computations. Otherwise, we can keep the equipment exactly at stations as they are chosen as A and B instead of keeping it some 10 to 15 meter away. So, let's assume that this particular station A is placed at the lower level and the line of sight is inclined upward the way it is shown here in this particular sketch. So, when the equipment is at station A, this true difference in elevation H should be equal to A minus B minus E. Whereas, when the equipment is at station B, this true difference in elevation H must be equal to A1 minus E minus this B1. So, here this error component can be worked out by A1 minus B1 minus into bracket A minus B by 2. If E is positive, the line of sight is inclined upward, and if it is negative, the line of sight should be inclined in the downward manner. Also, here the true difference in elevation H can be computed as mean of the staff differences as opted here. Here again, if H is positive, A is situated at lower elevation. If it is negative, A is situated at the higher elevation. So, as we work out that particular error components, the correct staff readings can be worked out as shown here, and we can place our diaphragm ring in order to give the correct staff readings. The concept that we discussed can further be elaborated by attempting this particular example. So here the Theodolite was set up between these two stations A and B 100 meter apart. The readings obtained are 1.65 and 1.21 respectively. The instrument was then moved at, say, distance D, which is 10 meter ahead of this particular AB. The respective staff readings obtained are 1.405 and 0.935. So let's compute about this particular staff readings on A and B so that the line of sight is horizontal. So when the equipment is at the midpoint, the true difference in elevation is worked out as 0.44 meter. As such, station B is higher than A. When the equipment is at station D, the Apparent difference works out to be 0.47 meter. This shows that the line of sight is not in adjustment. So let's assume that particular line of sight is inclined upward. Hence, as we go for similar triangles and as we determine EB minus EA by 100 should be equal to 0.01 E, which should be in turn equal to EA by 110 should be equal to EB by 10 as we discussed on the previous slide. Hence, EB is 0.1 E and EA is 1.1 E. So that particular true reading at A has to be 1.405 minus 1.1 E and true reading at B should be equal to 0.935 minus this 0.1 E. Hence, 1.405 minus 1.1 E minus 0.935 plus 0.1 E should be equal to this 0.44, which is nothing but the true difference in elevation. By solving, E works out to be 0.03 being line of sight upward. Hence, as we have this particular value of E, the correct stamp reading can be worked out as 0.932 and 1.372 at station B and station A respectively. So we can apply the check and we can confirm the computations that we did. The sixth and last adjustment is of vertical circle index. According to the requirement, the line of sight is horizontal when vertical circle reads 0 and the altitude bubble is centered. As already you have learnt about the constructional aspects of theodolite, there is index or T-frame centered over the Vernier axis of the equipment. It comprises of horizontal index arm, or also called as Vernier arm, and certain clipping arm perpendicular to this particular index arm, at the tail end of which there is a provision of clip screw. Whereas on the other arm there is provision of vertical clamp as well as vertical tangential screw. At the extremities of this particular index arm, there is Vernier C and Vernier D, which are in fixed position. The rotation of the telescope is in relation with this particular Vernier C and Vernier D, which in turn facilitates the movement of the vertical circle with respect to this particular Vernier C and D in order to take the vertical angles. There is a provision of this particular altitude level tube on the top of this particular T-frame. So all these particular elements are essential in order to discuss the adjustment of vertical circle index. Here we can keep the equipment say at distance of 50 meters and we can perform the adjustment. Initially, let's set this particular equipment with the face left condition and get it temporarily adjusted. Now center this particular altitude bubble tube and read the vertical Vernier. Again, change the face of the equipment and read the vernier as we center this altitude bubble tube. If the zero of the vernier scale is coinciding with the zero of the main scale, there is no vernier index and hence there is no need of adjustment. However, if the vernier does not read 0, it needs to be rotated by making use of clip screw so that it reads 0. Alternatively, after setting this particular vertical circle to read 0, we can take a reading on a staff held at about 50 meters away, once with face left condition and next with face right condition. If the reading remains same, the equipment is in adjustment and hence there is no need of adjustment. If the reading is not remaining same, we have to set the line of sight against the mean of that particular staff readings by using vertical tangent screw. Hence, now the telescope will be in horizontal plane. However, at this particular condition, the vertical circle won't read 0. Hence, without disturbing the telescope, we have to make the vernier to read 0 by using clip screw that is provided on this particular T-frame. As we move this particular T-frame, the position of the bubble will be changed. So we have to bring it at the center of its run by making use of capsule headed screws provided on that altitude bubble tube. Again, perform the test and if required, perform the adjustment till the test satisfies. So, thank you for your attention. I hope all the 6 adjustments that we discussed are clear to you. As we move ahead, we'll be discussing about the modern aspects for advanced surveying measurement that are applicable for land surveying. So bye till then, I wish you very happy learning. Thank you.